This video is going to be questions 6 and 7 of your notes. So now it's going to be the opposite way you just did. So the video before was taking a known pH of weak acid and figuring out the Ka value. Now I'm going to give you the Ka value of a weak acid, and you figure out what the pH should be of the resulting solution. So our acid here is propionic acid. I'm going to write that as just H-Pro. It says acid right here. You can write the whole thing out if you want to, but we'll just write it as H-Pro. I'm going to write my dissociation a little bit different. Instead of drawing my arrow and drawing H plus Pro negative, I'm going to do it with water. Remember, water is not part of your K expression, though. In this case, if we do that, we're going to say it forms H3O plus because the acid is giving to water plus Pro negative. So that's your conjugate base. Okay, conjugate base. Sorry about the bright spot there. I'll try not to write in that area if I can help it. So this tells us that we have 0.1 mole in 1 liter solution. So initially, this is 0.1 molar. Water's not going to be important in this, so we really don't need it in there. This is 0 molar, and this is 0 molar to start with. Here's our Ka value, and we're trying to figure out the pH. So think about this. Our Ka equals concentration of H3O plus. Remember, that's concentration of H plus ions. H3O plus is H plus ions, same thing. Hydronium ion, same thing as hydrogen ions. Times concentration of our conjugate base. Remember, these two will be the same. They're in a 1-to-1 ratio. How much of this that dissociates? Well, the same amounts of these. All over concentration of our weak acid at equilibrium. We know our K value is 1.3 times 10 to the negative fifth. So we can plug in equilibrium values for those. Well, we can say that this is going to dissociate by X number of moles, so we can go minus X, meaning at equilibrium will be 0.1 minus X. These are going to increase by X number of moles, so at equilibrium these are both X. So plug those in. This would be X, this would be X, so we can make that X squared over 0.1 minus X. This would be a key, something you'll do often. We would have to quadratic this to solve this problem. We're not going to quadratic. If you saw from last problem, remember last problem we did on the previous video, the dissociation of this is often very, very, very small. That means this X value is very, very, very small. Maybe 0.0001, something very small, which means if you subtract that from this value would not change much by subtracting X out of it. It's going to be very similar. So we can ignore the X in the denominator of these. There's something called the 5% rule. If an acid dissociates more than 5%, we need to quadratic and figure out what the answer would actually be. But if it dissociates a smaller amount than that, this won't change much. Our answer is going to be very, very similar either way. So as we're solving this, I'm going to cross multiply. So I'm going to take 0.1 times that, which makes this 1.3 times 10 to the negative 6 equals X squared. Take the square root of that, the square root of that. And our X value is 1.14 times 10 to the negative third, or 0.00114 molar, which would be our concentration of hydronium ions, or our concentration of H+. It's also the concentration of this. But we're mostly concerned about the fact that this is the concentration of H+ ions, because we want to know the pH. So to get the pH, take the negative log. So the negative log of this number, 0.00114. And our pH in this case is 2.94. So a 0.1 molar solution of this acid that has a K value of 1.3 times 10 to the fifth will produce a solution with a pH of 2.94. Now we may be 100th off or so because we ignored that number in the denominator. We're probably less than 100th off though. If we want to find the percent dissociation of that, our percent dissociation would be this. That's how much it dissociated, divided by 0.1. Which is going to give you like 1.1% dissociation, very, very small amount of dissociation for that acid. So there's one example. Another one here. So we have this weak acid. I'll write it as just H-asp. It's acetylsilic acid, which is in aspirin. So if we go here, put that acid in water, it partially dissociates. It does dissolve completely, but it partially dissociates into H plus ions plus this conjugate base. Again, the conjugate base would be that anion, that negative ion. Tells us the K value right here. So again, we can do the same thing. Okay, this is 0.008 molar initially, 0 molar, 0 molar. These are going to go up by X. This is going to go down by X. There's our change. At equilibrium, this would be 0.008 minus X. That'll be X. That'll be X. So we can set up our K expression. K equals concentration of H plus times concentration of our conjugate base all over the concentration of our original acid. Same thing. We're going to have X squared, which would be those two, or both X's over 0.008 minus X. And we can plug in our K value, which is 3.4 times 10 to the negative 4. Again, I'm going to cross multiply. We can ignore the X. Okay, ignore the X. See what we get right here. Cross multiply this times this equal X squared. So when I do that, I get, I don't know what I get, but here is, once I cross multiply and square root my X, which is my concentration of H plus ions, remember, the X is our concentration, H plus, it's also that concentration, but to get pH, we want to know this concentration, is 0.0016 molar. Well, in this case, if we would find our percent dissociation, 0.0016 over 0.008. So out of the original acid that was 0.008 molar, it produced that much H plus. So if we take 0.0016 divided by 0.008 and move the decimal over 2 places, that's 20% dissociation. Okay, so I'm only showing you this. If our percent dissociation is greater than 5%, we cannot ignore this X value down here. We have to figure out what it would be. It means we have to quadratic. I will not make it quadratic. We've done that in the past. So we'll stick to problems where it's like the one up here, it's less than 5% dissociation. Have a good day.